Can you hear me? Okay, everyone?
Yes.
Okay, great. It worked. Let me just see how many people we have. 59. Waiting room. Hold on. Okay. 61. All right. Good. I want to make sure this thing's recorded too. It is recording. Good. And all right, I think that's 67. All right. First thing, when I share a screen, what happens is this, it really shrinks everybody down to about 0. So I'm going to try to spread this so I can at least get some visual confirmation about what you guys are thinking and feeling. Can I hear you? I heard somebody.
Do that pork shit, and I haven't done to actually get stuff in pork.
I mean, I'll go with you.
That's the issue. Let's go.
Chun-Li Tang's kind of a cool name.
All right, I think we're ready to go. First, you can unmute yourself if you have a, wait a second. All right, you can unmute yourself if you have a question. Last time we were talking about grounding and how to use Kirchhoff's current law to find, and I don't know what's going on. I'm hearing myself. But does anybody have any questions?
Can you work through problem 50 from the homework?
250?
Yes, sir.
Yeah, I'm going to redraw it, all right? Everybody with me? All right, this is problem 250. Most of these problems are fairly straightforward. However, can you all see this, first of all? Can you all see the shared screen? Just tell me in a nutshell if you can or can't. Okay, good.
Yep. Yeah.
Good. This is problem 250. I'm going to recopy it. It has a 2 milliamp source. And then it has 1K. I'm sorry, that doesn't work very well, but it's 2 milliamps going up. Then it has 1K ohm this way. Then it has 1K ohm this way. And then it has 1K this way. It has 1K this way, all right. And then it has 12 volts. I'm going to show you a few things about this one to make you happy. And these are in ohms, of course, this 1K, that's 2 milliamps. And this is a problem, even though it doesn't say ground the bottom, and I call it a bottom rail, but you all see this point right here, class, the lower point. Let me try to get a different colored pencil or pen, pardon me. You all see that? Now, this is one way it's important to do grounding. Always use this if it's available. Can everybody see what I've got right here, just to make sure we're on the same page? Good? Okay.
Yes, we can see it.
Just thumbs up, something like that. All right, ground this right here. That means it's at 0 volts, right? Now, the next thing they have is they show for 250, they put V1, V2, and V3. You see how they have V1 here, then here V2, and then V3. You all see that, class?
Out of focus.
Oh, God.
It's cloudy again.
Yeah, that's out of focus. It should be in focus in 1 second. 1, 1000, 2, 1000. Come on. There we go. All right. I mean, I hope you can all see this. This is just a redraw of the circuit, right? Everybody? Now, look, this 0 volts means this entire lower conductor that I put on there, I put the ground symbol, is going to be at 0 volts. Now, he didn't say this explicitly, but it means all these voltages that are shown here are with respect to this being 0 volts. Do you all understand that, class? Everybody give me a thumbs up for those that have their cameras on, so at least I can, okay, I'm seeing unanimous consent here. Now, if that's
Could you explain that? Like, I didn't really follow grounding last time. Could you go over that?
You know, voltage is like pressure, right? And pressure is always relative between 2 points. Isn't that right? If you think about it, pressure by itself means nothing unless it's a measure with respect to something. If something is 30 pounds of pressure per square inch above a certain point, then you know that that's the difference, and that difference will drive the flow of water or air. Correct, class? All right, if this is 0 volts, if I'm calling this 0, and I call this V3, it means this point is going to be measured with respect to this being 0. Now, if you just look here and do this the way we did the voltage summing, I'm at 0 here. When I go through this 12-volt source, is that an increase or a decrease, class?
Increase.
Decrease.
It's an increase of 12. What is V3? Just by inspection, isn't it 12 volts?
Yeah.
You all see that?
Yes.
Now this
Quick question.
Excuse me?
How could you say that it's 0 volts right there?
Remember what voltage is. It's relative, right? It's like a mile marker on a highway. You can put 0 anywhere. It's just when you put 0, everything's measured with respect to that. Make sense?
Yes, thank you.
All right. Now, if that's 0 volts, this is 12 volts, isn't it? That's what V3 is. By definition, you all agree with that?
Yes.
Now, this one's made to make you think. And I'll admit I do this all the time. You see how we have the 2 milliamps? It's a known current flowing in this direction, isn't it? Class? Now pay attention to this, everybody. This is where it gets important that you're real attentive. Now I gave this, and I'm going to break out right down here to show you something. I told you that if you have a resistor R, and it had some voltage here, V1 on this side, and V2 on this side, and I'm putting the plus minus there for a reason. If I wanted the current flowing from the positive to the negative side, I would say that I1 here was equal to the voltage on the positive side minus the voltage on the negative side. We know these voltages are measured with respect to the ground, though, don't we, class? And then divided by the resistance. Do you all see that? Give me a thumbs up if you do. I'm trying to just make sure that y'all can hear me and see me. Can somebody just tell me how many people are here? Because I don't have that available to me when I share my screen.
90.
90, perfect. We're almost at 100. We'll be getting there, I think. I mean, there can be technical difficulties. God knows there's all sorts of problems. Y'all with me so far? I'm going to do this example in its entirety. Now, here's where we do something a little different. we're going to use Kirchhoff's current law. And the technique is actually called nodal analysis, and it's something you'll be using extensively throughout this course. What I'm going to do is start defining currents, all right? We know the 2 milliamps is going up there, right?
Yeah.
That's
Can you
defined.
move it down a little bit?
Yes, I can. I mean, 2 milliamps is going up, and I'm sorry it's messed up there the way I drew it, but you all follow me, right? It's in this direction, 2 milliamps. Now this is V1. You all see if current is flowing into there, Kirchhoff's current law says that it has to be equal to the current flowing out, right? Here's where you have some freedom. I'm going to call the current flowing this way, for lack of a better term. Matter of fact, let me get rid of that orange marker because that probably is not going to show well. I'm going to call this current I1. Do you all see that there? It's from V1 down. Can you all see that okay?
Yeah.
Now I'm going to call this current I2. You're going to see this. This is very similar to what mechanical engineers do and aero and probably, I'm going to guess textile. Well, it's not textile anymore, but any kind of industrial engineering will have something akin to this in a flow process type thing. Now I'm going to call this current here I3, just arbitrarily. It could be IA, IB. It makes no difference with how you designate them, as long as they're unique. And I'm going to call this current I4. You all see that, class? Everybody with me?
Yes.
Take a good look. Make sure you understand what I've done. Arbitrarily assigning these currents. And now down here, what I'm going to do is write Kirchhoff's current law. It's really called nodal analysis. All right. Now, what this means is simple. Nodal analysis. Anytime you have a node, it's a point where current can enter one way and more than one way come out. Isn't that right, class?
Yes.
So here's the first node. Just call that N1. Current can flow into it and come out two ways. Correct, class?
Yes.
Take a good look. Make sure you're convinced.
Slide it up a little bit, please.
Oh man, thank you so much. This thing irritates me because if I can, let me just see if I can decrease the magnification a little bit. Problem is, and it shrinks the size of the page. Sorry.
I had a quick question. How do we know that there's a ground on the bottom when the diagram from the problem didn't show it?
They didn't put it there. You put it there from always. Got it? It's just like in the real world. You put it there. It's implied. You'll assign a ground. Whenever you see a V that's got no point with its reference to, you apply a ground. And it's always on these problems at the very low point of the circuit. I call it a bottom rail. It's the thing that's connecting all these parts to ground. Are you with me? It'll become more apparent as we do problems. Everybody with me so far? All right, now pay attention to this. Nodal analysis, I'm going to put node 1. At node 1, what flows into node 1? Just look. I hope you can see this. If you can't, just look at your the problems I assigned you, 250. What flows into this node as I've shown this? That's node 1. Class?
2 milliamps.
2 milliamps, right. So I'll put down 2 milliamps is going in, right? Now what flows out? Take a look. Class?
I2.
Yeah, I2, but I like to put I1 first. Plus I2. I try to get standardized on this. But you're right. You can put I2 first if you all agree with that, class.
Yes.
All right, now this thing's starting to irritate me. Now the next thing I do is I replace I1 and I2 by the voltages and resistances. This is Kirchhoff's current law, right? Current going in is equal to current going out. But now I define currents in terms of the unknown voltage. 2 milliamps is 2 milliamps, isn't it, class? Right? It doesn't change. That's a constant. What is I1 in terms of the unknown voltage? Take a good look. The voltage on the side where current's entering is what, class?
V1.
V1 minus the voltage on the side it's leaving. What's the voltage down here?
0.
It's 0, and that's why you put a 0 reference, because anything minus 0 is just anything, isn't it, class?
Yes.
So just leave it as V1 and get rid of that. So it's V1 divided by R1, which is 1K, correct, class? And I dropped the ohms, but it's 1K ohm. It's 1,000, isn't it, everybody?
Right.
Technically, it's ohms. I drop that usually. Now, that's the current going this way. What is I2? Take a good look. What is I2, class?
V1 minus V2 over 1K.
Very good. Exactly. Over 1K. Does everybody see this? I want you to make sure you do. This is the basic thing involved with nodal analysis or using Kirchhoff's current law to solve a circuit. Everybody? Okay, I got it. Give me the thumbs up thing because I can see that. All right, for those of you with cameras on in the first page, I think we have 4 pages. I can see it and it's unanimous. Now, here's what I do. You don't have to do it this way, but I like to make things as simple as possible. You see how I'm dividing by 1,000 on both sides? And this is times 10 to the minus 3, isn't it? Or it's 1 over 1,000, right? So if I multiply everything by 1,000, what do I end up with? That goes, and the milli goes. So I have 2 amps equal to V1 plus V1 minus V2, don't I? After I do that? You all see, I just multiplied everything by 1,000, both sides. Correct, class? Everybody got that? I mean, you're engineers, you're smart people. This should be obvious, but I have to make sure, mainly because of the technology. If I was in front of a board and had you guys, I could take one look and know if you got it or not. All right, now we combine terms, and you see that 2 here is equal to 2V1 minus V2, correct?
Yes.
That's a first equation that governs the system. So box that, just box it, and call it number 1. This is my suggestion. You're creating a linear system, basically, linear system of equations. You got me? Now, that's node 1. Now for node 2, and I'm sorry, I'm going to have to go back and forth on this one. For node 2, right? Now I take a look at that. I'm bringing back the circuit. For node 2, look at it. It says I2 going in is equal to I3 plus I4. Doesn't it, class?
Yes.
So I'm going to go ahead and write that. And I'm going to put I2 is equal to I3 plus I4. Everybody good? I want you to write it and just think about what I'm doing. I'm equating whatever flows into a node flows out of it. Now, I'm going to pull this back. And I'm going to put the current in terms of the voltages. Unknown and known voltages, all right? Ready? All right, what is I2 equal to in terms of voltages? Just take a look at this. Anyone?
V1 minus V2 over 1K.
Divided by
1.
1K. All right, now I'll put that down here. So I'm going to put it's equal to V1 minus V2 divided by 1K. That's I2, correct? Everybody?
Yes.
Yes.
All right. What is I3? I hate doing this, but I have to. What is I3? Just by inspection.
V2 minus 0 over 1,000.
Just V2 over 1,000, okay? That's where that ground really gets rid of a lot of terms. If I made the ground 5 volts, you'd have a 5 volt everywhere, wouldn't you? All right, but 0 is a nice number because it doesn't do anything when you're subtracting or adding it. So here, it's going to be I3 is simply V2 over 1,000, right? Well, 1K, plus what is I4? Take a look.
12 minus V2 over 1,000.
I4 is going this way, isn't it? What do we do?
Minus 12.
Oh, V2 minus.
Right, the voltage on the side the current's entering minus the voltage on the side the current's leaving. I'm glad you made that mistake. You'll see people make that all the time. It's called a concept mistake, and it's worth at least 50% of the problem, if not a lot more. Concept errors you get clobbered for. The grader's here somewhere, I think, but you will get murdered for those. Now, if you make a mistake and you have a right answer somewhere and you copy it wrong or a decimal point, that's a minor mistake. Concept errors, you lose almost all credit, right? So you have to have those exactly right in this course. Sort of like in your mechanical engineering courses. When you had thermo, PV equals nRT was the ideal gas law. If you had PT equals RVC or something like that, you get 0 credit, period. It's the same way here, all right? You got it? It's concept. Back here, I4 was equal to V2, right?
Mhm.
Minus 12, because 12 was the voltage with respect to 0 divided by 1,000, right? Y'all agree that that would be the equation? Now, I want you to make sure you see this before I move on. I only have to make it clear one time and then it becomes easy, but I have to do it, make it absolutely clear the first time.
Why was the I3 V2 again?
I3 is what? Now, I want you to take a look, whoever asked the question. It's the voltage on the plus side where the current's entering minus the voltage on the negative side, right?
Yeah.
Whoever asked that. Garrison, you asked that, right? Well, what's the voltage on the negative side?
0.
All right. We don't include. You don't need that, right? V2 minus 0 is V2. That's one of the reasons we always make ground 0. It eliminates a whole lot of terms. So now I come down to here. Anybody want to take a guess what my next step is?
One equations, two unknowns.
Before that, what do we do down here? Somebody, come on.
Multiply all of them by 1K.
Yeah, by 1K. In other words, get rid of the K. Agreed?
Yes, okay.
Mhm.
Now, the next part of it is you need to get all the unknowns on one side and all the knowns on the other of any type of linear system of equations that you hope to solve. Y'all with me on that?
Yes.
You don't actually have to do this, but it serves its purposes. So for this one, I'm going to leave the 12 on this side. I could take it to the other side, but 12's right here. You all see that, class? Minus 12, to be honest. Right? So I'll leave that alone. Now you'll notice I have V2 plus V2. That's 2V2 on the right-hand side, correct?
Mm-hmm.
Yeah.
When I take it to the other side, it's minus 2V2, correct?
Yeah.
Yes.
And added to minus V2, it's going to be V1 minus 3V2, therefore is minus 12. Now I'll tell you a trick I'm going to do in 1 second once you get there. That's the second equation. Y'all follow me?
Yes.
Yes.
Yeah.
I'm going to give everybody a second to think it through, because I know that there may be lag and God knows what else the problems may be. I'm making sure everybody has a chance to understand what I've done and why I've done it. All right, next, what I'm going to do, and I do this, you don't have to. I don't like negative signs. This is just me. There's no reason for you to do it unless you feel comfortable about what I'm doing like I do. I see there's 2 negative signs, 1 positive. I multiply both sides by a negative, and I get that, just to reduce the number of negative signs. And this is just me. You do not have to do this, okay? With me? Now, by this time, you've solved linear systems of equations over and over and over again. This is one of the easiest ones. There's no complex numbers. Everything's simple. So I'm going to create it in terms of a matrix. And I'd appreciate in the tests and quizzes that you always get the system of equations numbered, and then you do the next step, which is create a matrix. Now you can see here, really 2 should be on the other side. How about if I put it on the other side? Okay. I just rearranged that, okay? And now I'm going to create a system of equations. You okay with me?
Yes.
All right, so when I do this, I'm going to go ahead I'm going to put, first equation was 2, and then it's minus 1.
Could you slide the paper up a little bit?
I will. I'm 2 minus 1, and then it's V1, V2, right, is equal to, and that's 2 and 12. And the second series of equations is minus 1 and 3. Y'all got that, class?
Yes.
Now, you have calculators. Back in the day, when no calculators were used in this class, people would use something called Kramer's rule to solve this. How many remember Kramer's rule? Anybody back in the day when you took linear systems, or whatever they call it, linear algebra, right? Linear algebra. You had to learn those things. I don't expect you to do that, but you all have calculators, right? And your calculators can do this in a heartbeat, correct, class?
Yes.
All right. Now, if you want to, you can use Kramer's rule to get this answers, but I strongly encourage you to make use of your calculator. If you want to, you don't even have to do this for this one. If you look at this, if I wanted to do something and solve this thing, if I multiply the bottom one by 2, right, I would get 2 here, then I'd get 6 here, and then I'd get 24 here, correct? And then what could I do? I could add them, couldn't I? What would I get? I would get 5. I mean, if you, excuse me. For that one, I would have 2 minus 2, the V1s go. Then I would have
5v2 equals 26.
You agree with that? Whoever said.
Yes.
All right, now could you solve for V1 as well?
Yeah, substitute.
Well, if you have V2, you can stick it here or here and get V1, correct? Now, how many have used your calculators to solve matrix equations? And I want to see the hands here. How many have used your calculator to solve matrix equations? Give me either a thumbs up or hands, some way of indicating you have. 1, 2, 3. Well, it's hard to see when nobody's got any kind of information on blank screens, but I'm assuming everybody has the ability to use their calculators and they can figure it out fairly rapidly. I don't have my calculator from my office here. I have a very old actually it's probably 91 TI calculator that I use. Most of the people these days, no, I'm sorry, HP calculator that I use. It's an old HP. Most of the people these days have TIs, right? Texas Instrument calculators. Am I right about that? How many have TIs? Just let me, I've always tried to figure out who I'm talking to. Well, if you have a TI, just go online, type in TI 89, TI, and whatever it is, 93, TI 84, TI, whatever it is, and then just type in after that, solving linear systems of equations or solving linear algebra equations, and there'll be a cajillion things. I prefer you go to YouTube and take a look at a link, and they'll show you exactly how to do it for your calculator, including with complex numbers that come later. Okay, everyone? Now, I'm trusting, because there's so many different calculators. There's 84s, 89s, 93s, then there's, what's the Inspire or something like that? Isn't there one something? I forgot the name of it.
It's Inspire.
Then there's Casios, and then there's old people like me that have HP calculators, and there's so many variants. I can't be responsible for that. But one thing I can tell you is, worst case scenario, if you don't know how to use your calculator, I can go over Kramer's rule with you, and I'll be happy to do that, and it's trivial, but you have to know how to solve matrix equations. So the next logical question somebody's thinking about is, well, do we need to just do 2x2s, or should they be 3x3s, 4x4s? On an exam, you'll get nothing greater than a 2x2. Did y'all hear me? Or quiz? Nothing greater than a 2x2. But you need to be able to solve that quickly and efficiently and accurately. if you put a matrix down, if it's right, but the answers are wrong, at most you'll get 50%. In this course, like many others, simple problems that have simple solutions are graded really exactly. It has to be completely right. Now, more complicated problems, things that have many more things going on, there's more leeway. But something this simple, if you have the right equation, wrong answers, then you're going to at most get about 50%. Am I absolutely clear about this? So you can't be sloppy. Now, I'll just say this too. I don't agree with people that have multiple choice tests for engineering. I don't do that. I think, frankly, it gives credit where it's not due. Some people don't know what they're doing, but they guess right. I'm just telling you this. And some people know what they're doing and they miss one little thing and they get 0 for a problem. So I don't do that and I won't do that, but I know Dr. Birch does it in mechanical engineering. There's other professors now because of Zoom and Honor Lock that are doing that. But I'll tell you right now, I don't do that and will not do that. You have a grader that is listening to me right now, hopefully, that knows that I don't approve of that, but he will get a template to grade your stuff by. And the easier the problem, the harsher the grading. Follow me? So you can't be sloppy. You don't get partial credit if you put down scribbles and stuff like this. You have to have a logical flow of everything. It has to be neat and clear. And if there is a mistake where for whatever reason you got the right answer here, you copied it up into a space wrong, there'll be an allowance for that. But again, exactness is rewarded in precision, just like in the real world. You know, I'm telling you that because I have had people argue and argue and argue. Oh, but back here, I just forgot this resistance. And if I would only include, well, the whole point is you didn't. And the idea is if you're being paid a lot of money to build a bridge, it can't collapse. The owner doesn't want to hear, well, I forgot a pylon here and there. You can't get away with that here either. Okay. I'm not trying to be cruel. I'm just trying to make you know that this is serious. Another thing that's going to come up all the time is, well, and people ask this in various ways, that am I going to use Honor Lock? No. But you're going to have, unless they come up with a different version of it, unless you have your cameras on and I can see you or my grader can see you at all times, if for whatever reason there's a problem, and it's especially a reoccurring problem, then you'll probably get a 0 for that quiz or test. Wait a second, we're not even going shelter in place. You're going to be up there. Hopefully we won't go shelter in place quite that soon. But if you're up on the university campus, there'll be a couple of different tests created. They won't be the same in quizzes. And you'll be seated such that there's the type of cheating that could occur is about 0 chance of happening. And it will be closed book, closed notes, but your calculators you're allowed to have. Did you hear me? I'll get that question probably 100 times. You are allowed your calculators, no matter if you're just at home or if you are up there in Brown Koppel taking the exam or quiz. Clear? So know how to use them. Don't buy a new calculator and not figure it out before you get there. You get 0 credit for not knowing how you're doing things. And I'm just trying to be clear about this. All right. So that's how you do that problem. Whoever asked that, thank you. Did you have a further question about this or did this answer the problem?
Yes, that answered it. Thank you.
Oh, by the way, what was V1? Somebody, I don't know what it is.
18/5.
18/5. And was V2 26/5?
Yes.
Okay. All right. And that's volts. Okay. And that's the answer. You can leave it like that here. Got me on that? Now that's perfect because here we apply Kirchhoff's current law to that problem and you should have by now seen how it works, right? I think it would be in the best interest of everybody, because that's what we're going to do, is do another problem using Kirchhoff's current law. Unless there's an overwhelming problem that you want me to do, something that's really burning at your heart. If you have that, I'll do that problem next.
I was going to ask if you could do 236.
Yeah. I'll tell you what, we'll do 236, then I'll jump into the next problem, okay? Whoever asked that. Okay, everyone?
Sounds good.
Okay. All right, this is 236. Some of you will get this in a heartbeat. It's been my experience that mechanical and aero engineers have some course in their background that makes this stuff simple. I don't know what it is, but they look at this. I don't know if it's hydraulics or what, or incompressible fluids, but you look at this stuff and it's like, this is easy. Well, there are people that don't have that, so bear with us. For this one, it says that you have V1 here is an unknown, so we don't know that, but there's 4K here, 4 kiloohms there, and then there's 8 kiloohms here, and then there's 4K ohm here, right? Now those are in ohms. If you want, I'll put that on. I don't usually do that because frankly, it's overkill. If you see a resistor, it's in ohms. Everybody got that? All right. Now I'm going to go through this in the way I would do it. And it's really just more or less finding out what you can find out with what you got available. They say this is I1, correct?
Your screen is out of focus.
Thank you. They say this is I1, correct? And they give a value for I1. 2 milliamps, correct? This is actually VS in the book, I guess. Isn't it, class? All right, so they tell you this is 2 milliamps, correct, everyone? Take a good look. Do y'all agree with that?
Yeah.
All right, now watch. We've got a resistor, and we know the current through it. Do we know the voltage across it?
Yes.
Yes. What is it? It's 2 milliamps times 8K or 16 volts. Do you all agree? Right?
Yes.
16 volts, right? Now, isn't that 16 volts also across the 4K? Because they are in parallel, right? Y'all see that, class?
Yes, sir.
All right, well, if there's 16 volts across 4K, what's this current? I'll call it I2 for lack of a better term. It would be what? The voltage is 16 divided by 4K, right? Or it would be 4 milliamps, wouldn't it, class?
Yep.
Everybody? All right. So I2 here is 4 milliamps. I'll call this I2 equal to 4 milliamps. Sorry, I'm writing with orange, but I think you can see it. If you can't, I'll change. And this current I1 is 2 milliamps. That's by definition, right? All right. Everybody with me? Who asked this, by the way? I couldn't tell.
That's me.
All right. John? All right. Now, therefore, how much current is flowing through that 4K? I'll call it I3 for lack of a better term. Anybody? Well, what flows in flows out, right? I3 is flowing into this node right here, isn't it, class? Y'all with me? Right?
Yeah.
All right. The I3 is flowing in. We don't know what it is. Well, how much is flowing out? I1 is 2 milliamps, right? And I2 is 4 milliamps, right? And therefore, that's 6 milliamps, isn't it? Whoever asked. Y'all agree with that, class?
Yes.
All right. Well, 6 milliamps is I3 right here. Give yourself a second, write it down, think about what I'm doing this sequentially. I'm finding out what I can get and see where that leads me. Now, having said that, could anybody hazard a guess what my next step would be? Anybody?
The voltage source output across the 4K resistor.
Well, the voltage across the 4K, it's not really an output. So what would it be? You're right.
I times R.
Yeah, but 6 milliamps times 4K is?
2.4.
24 volts.
24 volts, right? Plus to minus 24 volts. Sorry, it's kind of, it's drawn in orange and it's there, but you all see this. Give me a show of hands so I can see if you do. You got it? It's unanimous on this page. All right, now we want VS, right? I want you to please take a look at this in focus here. When I look at VS, remember, this is something I didn't get at in a hard way. I mentioned it sort of in passing. If you want the voltage between any 2 points, you start at the negative point. I want it across this, right? I want VS. Start at the negative point and then add all the voltages till you get the positive. That's the voltage across VS. Now pay attention to this. I'm starting here. I got 0 volts. I come over here. I get a voltage increase of 16. Do you all agree with that? Went from the negative to the positive at 16. Do you all agree with that, class?
Yes.
From here to here. What about from here to here? It's another what? Went from a negative to a positive, say it. Increase of
8.
Isn't that 24? Isn't it 6 milliamps times 4K, class? Right? Didn't we agree that that was 24 volts? Agreed?
Yes.
Right? Okay, so this is plus 24, right?
I have a question about that. How do you know across both of those which side is the positive and which side is the negative?
Current enters the positive, leaves the negative, right?
Gotcha.
And we started with I1 defined as 2 milliamps. Are you with me, everyone? All right, so what's this going to be? Well, 24 and 16 is, class?
40.
Thank you, 40 volts. I don't know what the answer is, but you all see the method I've used to do this. Okay, everybody?
Yeah.
Quick question. Why do you not add the other 16 with that parallel resistor?
Remember, if voltages are in parallel, they're across literally the same, sorry, if resistors are in parallel, they have the same voltage across them, correct? Think of it as a pressure. If you have a pressure difference that appears across 2 components, and I want to get the pressure difference across an entire system, an air conditioning system, I just need to go over one of the pipes that's in parallel, right? Find the pressure change there, add it to the pressure change here, right? Don't I, class? How many understand that? Remember, voltage is like pressure, right? If you have 2 components that are across the same pressure source, and we want to know how much pressure is in the total system, we just add one of those pressures, differential pressures, to the total sum. Got it? Everybody?
Yeah.
Thumbs up if you do. It's hard enough to read because I got probably only 1/4 of the people I'm looking at right now have screens on. And that's okay. I'm just trying to make sure that I'm reading the class right. And for whatever reason, if you're not getting this or there's a problem, especially a technical problem, let me know. Like last time it was a disaster.
Sir,
hopefully this is okay. Yeah.
can you just explain the first half of this question again? I just went to the bedroom and missed the first half.
All right. It gives us a circuit. Do you have access to the homework?
Oh, yes, sir.
It gives us a circuit where there's 8K in parallel with 4K. And these two are in series with 4K. And there's an unknown source VS, correct?
Yes.
Now, I1 is given as 2 milliamps. I hope you can see this, right?
Yes. Mm-hmm.
Well, if I1's given, then we know the voltage across this 8K, don't we?
Yes, sir.
We know 8K times 2 milliamps would be 16 volts across here, correct? Everybody? And that has to be across this 4K because these are nothing but wires, right? That have no ability to resist current. So that potential is across the 4K as well. Do you all agree with that?
Yeah.
And therefore, if that potential 16 volts is across 4K, we know the current through here, which would be 16 over 4K, or it would be 4 milliamps, wouldn't it? All right?
Yeah.
Now, if If 2 milliamps flow this way and 4 milliamps flow this way, both of them have to come through this 4K, right? And that would be 6 milliamps, right? So 6 milliamps times 4K would be 24 volts, right? And therefore, we can find Vs. We start at the negative terminal. I'll say this a couple of times. I go around, so I get to negative. From here to here, it's plus 16. From here to here, it's plus 24, or it's 40 volts. And hang on, somebody had a question, or they typed something in chat. Oh, yeah. Okay. Everyone. Y'all with me in this class? All right. Before I just move out, there were a couple problems about resistances. Y'all remember those? I gave you to calculate the equivalent resistance. How many remember seeing those and did them or tried them? They, to me, were very simple and obvious. Were there any questions at all about the resistance problems at all? Or you just had to calculate the equivalent resistance? Anybody at all?
Was that what question 2.39 was asking? Because I couldn't tell.
Yeah.
Okay. Would you mind going over that?
I'll tell you what I'm going to do. I'm not even going to bother rewriting. I'm just going to show you this. All right. Is this okay?
Mm-hmm.
All right. Now just look. Here's the question. Find out RAB. By the way, these are the kind of things that it should be almost reflexive by the time you get done with this course. You take one look at this, it's almost laughable how easy it is by the time you get done, but not right now. So if I look at this, what I always do is find out what I can add in series and parallel, combine them, and then replace the two resistances with one. Everybody follow me on that? That's the way we do it. And you've had this in physics, by the way. You've had this. All right, ready? Whoever asked it. All right, now where do you go? Well, over here, you see how I have 4 and 14K in series. Did you see that? Whoever asked? I'm not sure who asked, but I
Yes,
hope.
yeah.
All right. So that's going to be 18K ohms, right?
Mm-hmm.
It's in parallel with 9K, isn't it?
Mm-hmm.
So 9K is in parallel with 18. What's that equal to? Well, it would be what? 1 over 9K plus 1 over 18K, right? Which would be 3 over 18K, or would be 6K. Do you agree with me? You can do the math.
Mm-hmm.
How many agree with that? So I shouldn't do this, but I'm going to anyway. I can replace all this with a single resistance of 6K. Can't I, class? Now, how many see that? It'll take a while for you to get to just take one look and know this, but you will. If you're good students and you do the homework, you'll be looking at this as a joke by the end of the semester, trust me. All right, now if that's 6K, that's also in series with 4K, correct?
Mm-hmm.
Which is?
10K.
10K. 10K from here to here. Do you see how 10K is in parallel with 10K?
Mm-hmm.
10K in parallel with 10K is?
5K.
5K. Okay. Y'all are right. You okay with that, class? Now, I'm going to give you one piece of advice. Do as many as these resistance problems. I'll give you all. I gave you all the problems I have in front of me here, and they have solutions at the end. All right, that was in the first homework. All the problems in chapter 2 and the solution. Do as many as you need to, so it becomes almost a joke looking at them. You can take one look and know what to do. Now, some of you know what I mean, where it's just, oh, come on. It's like adding 2 plus 2, then 2 plus 2 plus 2, stuff like this. It'll be that simple. I'm not trying to make this seem trivial, but I'm just saying that's the level of confidence you should have in solving these before you move on. And some people get it in a second, but others don't. And I'm just warning. Now, I want to do one other thing before we move on, and I go through some more Kirchhoff's really nodal analysis. I want you to take a look at problem 40, everybody. You all see this? Now, here it's important that you note where they want the resistance between A and B. Do you see that? Between A and B. Got it? They don't want the resistance over here. They don't want the resistance over here. They want the resistance between A and B, these 2 points. You all with me on this? All right, now to do this problem from A to B, current would have to flow this way, or current would have to flow this way, or current would have to flow this way, right? Those would be the possible paths current could take between A and B. Agree? With me? I want you to listen. Now you see that that 6 and this 6 would be therefore in series. Can you all see that? Right, so 6 and 6 in series would be 12. And 12 would be in parallel with 6, correct, class?
Yes.
All right, so 12 in parallel with 6 would be what? 1 over 12 plus 1 over 6. That's 1 over what? 3 over 12, right? Or 1 over 4, or 4K. So between here and here, it would be 4K. If you don't know the math that well, if you didn't see this, just do the math. It's really what? 1 over 12. Maybe I better put this down here. The math is this in a nutshell. It's simply 1 over 12K plus 1 over 6K. The common denominator on this, or the denominator you can use, is 12K. So that's 1 over 12K plus what? 2 over 12K, correct? And that's 1 over 3 over 12K, or that's simply 4K, isn't it, class? Y'all with me on this one? I'm sorry, I don't mean insult intelligence. I do this because sometimes people are sleepy on Friday for whatever reason. Anyway, that's how you get it. Now, getting back to this one. From here to here, it's 4K, right? I'm going to show you a trick. You agree with that? How many do? Thumbs up or some way of indicating. Now, what do you notice about this circuit? From A to this point is the same as B to this point, right? Y'all see that?
Yes.
The whole circuit's parallel. What can I replace this with without ever calculating a thing?
4K.
Okay.
4K. So I have 4K to here, 4K to here. What's the resistance between A and B?
8K.
8K, right? Y'all see that? Show of hands if you do, or thumbs up, some way of indicating. All right, I'm getting through to you and I'm not trying to bore you, but I have to be clear about these things because there are some people that are unsure. They don't quite feel comfortable. So I have to make sure you see it. Got it? And if you got a good instructor, he's done this. Whoever's talking, go ahead.
Yeah, sorry. So at the bottom there, you said it's 8 instead of 2. How are those not in parallel?
Parallel would be the same potential crossing. Here, the same current has to flow through them, right? Right? Because between here and here, we're going to have one single resistor, correct? Between here and here, right?
Mm-hmm.
And then between here and here, one single resistor. The only way current gets from A to B is through both in series.
All right, that makes sense. Thank you.
Okay. All right, cool. Next, back to Kirchhoff's current law. Now this is real important, and it's called nodal analysis. That's what it's really termed. It's the most important. I talked to Dr. Gross, who wrote your book about this. There are a lot of different analysis techniques, but nodal is probably the most important. So we're going to use nodal analysis, and here I'm going to ask you to do with me. I'm not sure if I assign this or not, but I'm going to do problem 245 first. Now, was that in the assignments? I don't recall right off the top of my head. I can find out, but I mean, I've got
it. Wasn't in the ones we did last night.
Okay, good. We're going to do it. So this is 245, and I'm going to just redraw it. Y'all see it here?
Yeah.
I'm going to show you a trick too in a second, but I'm going to go through this the normal way. Now here it says use nodal analysis. It doesn't put a ground on there. It doesn't show unknown voltages. You follow me?
Yeah.
It's like something you would get if you were looking at a schematic. So we're going to introduce values. So let me just show you. I'm going to redraw that and then we're going to work through it. You have 2K ohms out this way. This is 2.45. I keep on hearing people jump in and out. How many people are here right now?
73.
Oh, mobile.
It's because it's already 150. It's 153.
Yeah, I apologize. Can you guys now just consider this the office hour? If you have to go, you go, but I'd like to finish this, okay? You okay? I mean, if you got to go, you go, and you can watch the video later, but or if you need to, but I want to get through this one problem with everybody. Are we good on this, class?
Yes.
Yes.
Man, I'm hearing some noise here. All right. And I apologize, didn't know it was over. So here, hey, it went okay, right? There wasn't a world-class problem. This is 2K. This is like an office hour. This is 2 milliamps. I bet you guys get this. See if you get it on your own. This is 2 milliamps. Here it's 2K. This is the type of problem I'd ask you. That's 2K. This is 4K. And that's 4 milliamps. I don't know how we went through that much, or that little, really, that fast. Now, it says use nodal analysis. Here's Baginski's rule and Irwin's rule. Unless they say otherwise, use nodal analysis. So first thing we do is ground that bottom one. That's 0 volts. There's the first thing. Everybody got that?
How do you know that you have to ground it? Is it just if you're doing nodal analysis, you know you should ground it somewhere?
That's exactly right. As a matter of fact, if you don't ground it, you're basically wasting a huge amount of paper because you're going to introduce constants you don't need. All right. Always ground it, whoever asked that, okay? Unless they say use a different method, and I'll get to that much later in the course, okay? So here it's 0 volts, right? Now, what did they ask in this problem? Find I naught. So this is I naught. That's what they're after. But here's how we're going to get it. We're going to introduce a few things. How many am I down to now? Am I under 50 or not?
You're at 54.
54, yeah.
I'm okay, that's it. Well, the next thing we have to do is put some unknown voltages. How many see that's a node? And I'm going to label that V1. You agree with me?
Yes.
Yeah.
And I'm going to label that V2. Now, if you want to label it VA and VB, knock yourself out. It's immaterial what you call them. You good, class?
Mm-hmm.
Yeah.
Now, I've got that. We're not quite there yet. Now, the next thing after that, I am going to label currents. I know I naught's there. He labeled that, right? So I'm going to label this as just I1. It's arbitrary. If you like IA better, go for it. Or I gamma, if you're a frat person or sorority, doesn't matter. Just something unique. Here, I'm going to label this I2. That's I naught. That current's already labeled, isn't it, class?
Dr. Baginski, how do you know which direction to do the current like that?
You can put them any way you want because we're going to use Kirchhoff's current law. Some of the currents going into is equal to some of the currents going out of. That's it. Okay?
Okay, thank you.
And you might get a value that's negative, but no problem. Now that's node 1 and that's node 2. You don't have to label that, but I do at this point to make sure we're clear. So for node 1, look at the currents. What does the law say? What flows in, flows out, correct? What's flowing in is 2 milliamps, correct, class?
Yeah.
Right?
Yeah.
I hope you can see it. And what's flowing out? I'm putting it on this side. Well, what's flowing out is I1 and I2, correct?
Mm-hmm.
You all with me on this?
Yes.
Yeah.
All right. Now, what's I1 in terms of the unknown voltages? What's the voltage on this side where I put the plus? Class?
V1.
V1. What's the voltage here on the negative where it would be coming out?
0.
0.
0. So here it would be what? V1 over 2K, right? We don't need the 0, do we? Class?
No.
No. All right. That's I1. Now what's I2? That's
V1
plus.
minus
Right. V1 minus V2. Keep going.
over 2K.
2K. Make sure you put the K down there, right? And that equals 2 milliamps, right? Whoever's talking, right? Everybody?
Yes.
All right. What might
Yeah.
I do next? Anybody?
Multiply by 2,000.
Both sides by 2,000. Do you all agree?
Yes.
Yeah.
Yes.
All right. And I'm doing that for one reason, because I don't like this. And this becomes 4, doesn't it?
Yeah.
Guys, how many see this? I'm not trying to drag this out. I'm just wanting to do this before I jump ship. Y'all with me?
Yes.
Yes.
All right, that's the first one. Now I'm going to turn it into a simple equation. I'm going to combine the coefficients like terms. So I got V1 and V1. That's 2V1 minus V2 equal 4. Box that and go first equation. Okay, that's number 1. Somebody help me over here. And I'm moving quickly, I know that. Now, what's the equation for node 2?
Would it be I2 equals IO minus 4 milliamps?
Equals I naught. How about I2 plus 4 milliamps? How about that? Because that's going in, right? All right, this is the node, right? I2 plus 4 milliamps equals I naught. Y'all give me that one, class? Okay. Next.
Push the page up a little bit.
I got it, man. I'm there. What is I2? I'm going to have to push it down anyway, just so you can see it, all right? What is I2, class?
V1 minus V2 over 2.
1,000, 2K, right? V1 minus V2 over 2K. Don't forget that, all right? Plus 4 milliamps, right? Equals I naught. What is I naught?
V2 over 4K.
Right. Y'all got that, class? Are you good with this?
Yeah.
Look, this is not hard, but I got to make sure you see. Everybody got that?
Yes.
Yeah.
All right. Now, what is my next step? If you like, we can multiply by 1,000 first, both sides, so we get rid of the K, right? And get rid of milli, correct, class?
Yeah.
And then I could multiply by 4, can't I?
Yeah.
That means there's going to be a 2 up here, so it'd be 2V1 minus 2V2, right? Right, now remember, I multiplied by 4, so it's plus 16, right? Is equal to V2. Do you all agree with that?
Yes.
Okay. And then finally, what am I going to do? Take the 16 to the other side. And then take V2 to this side, which would be a minus, right? So it'd be minus 3V2, correct, class? And then box that. I am trying to get you guys out of here without causing problems. That would be number 2. Do you agree with me?
Yes.
Now, y'all can take one look at these two equations and see if I subtract this from this, I get one equation with one unknown. Do you agree with that?
Yeah.
And can you all feel comfortable solving these two equations? Show of hands if you do.
Yes.
I'm assuming by this time in your engineering career, this is an automatic. So get used to using your calculators and solving these things correctly. I'm going to stop here. I know I'm over. Remember, this is technically an office hour. Does anybody have any additional questions about the lecture today or the prior material or the book or the course or God knows what else you might have questions about? Related to this course. I mean, don't ask me something about football. Anything at all? I'm here.
Sorry, can you repeat the last step of like from node 2?
Yeah.
Thank you.
Hold on. And enjoy your weekend, but please stay safe. You're asking how I got this?
Yes, sir.
Did you understand how I got this?
Yes.
All right. The only thing I did at this point was I multiplied both sides by 1,000. It got rid of the K here, the milli here, and the K here. Okay.
No, wait, sorry. Can you repeat that line, how you get that line?
This line or this line?
The second one, yeah.
This?
Mm-hmm. How you got it?
What is I2? All right, take a look. I2 is this, right?
Mm-hmm.
I2 would be V1 minus V2 over 2000,
Mm-hmm.
right? That's 2K, right?
Yes.
That's how I got this.
Okay.
The 4 milliamp is coming out, right?
Mm-hmm.
Whatever goes in comes out. So
Mhm.
I'm sorry, not 4 million. I naught is coming out. I'm sorry. I2 is going in, I naught's coming out.
Mhm.
4 milliamps is going in. So it's I2 plus 4 milliamps is what's going into this node. What's coming out is I naught. That's this.
Mhm.
Now, what is I2? Well, I2 is V1 minus V2 over 2K, right?
Mhm.
Right here. Sorry if it's not focused. It's there, right?
Mhm.
This is just 4 milliamps. It's flowing in, right? That should be 4 milliamps. And this is what? It's I naught. I naught is just voltage on this side, V2, minus 0 over 4K. That's how I got it.
Mm.
Got it?
Yes. Thank you.
And then I just simplified them. I multiplied by 1,000 first to get rid of K and milli. And then I multiplied by 4 to make it something where there's no fractions. And then I got this.
Okay.
Okay, everyone?
I have a question about node 1.
Okay. That's this.
About like the signs. So you have volts, you know, you've got stuff coming out in each direction.
Right. Remember, what does it say? Current flowing into a node is equal to current flowing out, right? Whoever asked. Agreed?
Yeah.
All right. Well, current flowing in is 2 milliamps, right? That's here.
Okay.
What's flowing out? 1 milliamp and I mean I2 and I1, right? I1 and I2, correct?
Yeah, I see it now.
I
It's
just had it
going,
reversed.
it's like a T. It's going
Right.
like that. Right?
That's it. And this is really hydraulics. It's incompressible fluids. Whatever flows in, flows out of the pipes. Doesn't matter how many junctions there are.
Yeah.
Or how
I
many.
hate hydraulics.
Okay, well, you can't
Yeah,
love it.
well, yeah. But I get it. I understand what you're saying.
All right, good.
Dr. Baginski, can you go over 2.25 from the homework, please?
Yep, 2.25.
Yes.
Yeah, okay, I'm going to just show you it here if you don't mind.
Yeah, that's fine. You don't have to redraw it.
So here's 2.25, and I hope you all can see this, right?
Mhm.
So they want V naught, and they give you this. They got 6 milliamps here,
Mm-hmm.
and they want I1. Now I'm going to show you something about this that's going to make it a lot easier.
Okay.
First, y'all see we can use current division to get I1. How many do of those left? Looks like we've got fewer and fewer. Y'all see this? We can use current division, right? We have 2 resistors in parallel and a current going into the parallel combination, correct, class?
Right.
All right, so we take current division says take the current flowing in to the actual parallel combination. That's 6 milliamps, right?
Mm-hmm.
Multiply it by the opposite resistance you want the current through. I want the current through the 6K, so I multiply it by 12K, right? So I have 6 milliamps times 12K.
Right.
And divide it by a sum of these two.
Okay.
So I'd have 6 times the quantity, 12 over 18, which would be 6 times 2/3, correct?
Yes.
And that would be what? 6 times 2/3 is what? 4 milliamps, correct?
Right.
Now, if you have 4 milliamps coming down there, don't you have the voltage across this? Right? Current times volt or resistance is voltage, right?
Oh, okay.
Isn't that right?
Yes.
Sure. So 6
Oh,
times.
I see. I see. Okay. So then you would just do 4 times 6.
Mm-hmm.
I'm sorry. Can you repeat what you said? So you're multiplying 6 by the sum?
Do you know current division? Do you understand current division?
A little bit.
Well, you have to understand it a whole lot. It has to be second nature if you're going to get through this course. I'm just telling you. So current division says if I want the current through a resistor and it's in parallel with another resistance, then what you do is take the current flowing into both of them. That's 6, agreed? 6 milliamps?
Yes, sir.
Then you multiply by the opposite resistance, which would be 12,000, 12K, right? And then divide it by the sum, which would be 18K, right?
Okay.
So 12K divided by 18K is 2/3, isn't it?
Yes.
2/3 of 6 is 4. 4
Yeah.
milliamps would be flowing through here. Okay,
Mhm.
that's it.
Mhm.
Since this is my official office hour, because I got you here, I might as well use it when I got people. Anybody got any other questions about this before we break off?
2.8 in the homework.
2.8?
Yeah.
Boy, okay. Oh, this one, you're going to kick yourself for this one. This is about as simple as it gets. This is stuff in high school. When I took electronics in 10th grade, they start with a problem like this. Remember what it says, Kirchhoff's voltage law says the sum of the voltages around any closed loop is 0. Isn't it, class?
Yes.
All right. And I gave you a trick to do too. I said that if you want the voltage between any negative and positive point, you start at the negative and you work to the positive and see what it is, right?
Mhm.
All right. Now, hear me now. I shouldn't be doing this, but I'm going to anyway. I want V2 first. Are you with me?
Yes.
I start here. I'm going to go around. What is this? An increase or a decrease of 4, class?
Which right there?
I'm going
Isn't
from here to here. Huh?
decrease?
No. I start at the negative. I ended up at the positive. It's greater by 4 volts, isn't it?
Oh,
Think of this as a
Mhm,
pressure.
mhm, mhm.
So I get an increase of 4, right?
Yeah.
And then I get an increase of 6.
Mhm.
And if I add them together, I get an increase of 10 from here to here, right?
Mhm.
And isn't that where V2 is? From this point to this point. So that is what? 10 volts just by inspection, right?
Yes.
Start here.
Yeah.
That's an increase of 4, increase of 6. And that's right at the positive. Started at the negative. It's 10 volts is V2. Got it?
Yes.
All right. Now, if that's 10 volts right there, what else do we know? Well, let me go ahead and try it. We could write a system of equations, but if I have 10 volts there, I got 4 volts there. And I want you to follow me on this, all right? If I start at this point right here, wait, let me do it. I know that's 10 volts. Now what I can do a couple of things. I'm looking for the quickest way to do this. If I go from here to here, I see V3 plus V1 is equal to 6. Don't I? Start here. That's negative, right? V3 plus V1 would be equal to 6, right? Let me just do it right. Try to do it right here. Hold on. I'm starting right here, and I'm getting V3 plus V1 is equal to 6. Agree?
We can't see the other one. The exercise.
You can't see this?
Yeah, I can see that one. Like, where do you say you start?
I start here. I've got, I'm going to get the voltage between here and here. I know it's 6. So I say an increase of V3, increase of V1 is 6, right? Because I know the voltage between those 2 points is 6, correct?
Yes, sir.
So that's this equation. Next equation, all right, if I take a look at this, I can go around this loop right here. And actually, I can start here at the negative, and I can say that.
We can't see.
Sorry.
Like, where you say you start.
Here's what I'm going to do is right here. I'm going to go at this point. I'm going to say increase of V4, then an increase of V3 is 12, right?
Oh, can't quite see it.
So I put 12 here is equal to V3 plus V4, right? That's this loop right here. Sorry. Agreed?
Mhm.
Yes.
And then I can go around this loop, right? You agree? Follow me, class? Well,
Yes.
I can start here and I see what? Minus V5, right? Plus V4, or better yet, I can go minus V5 here, start here. There'll be a decrease of V5. Then it can be plus 12 minus V3 equals 4. Equals 4. And here is the way I went. I went from here to here. Agreed? Now remember, we've got V2 solved. We've got that it's 10 volts, correct, class? So that means I have 1, 2, 3, 4 unknowns, correct, class?
Yeah.
I need 4 equations that are unique. I've got 3 of the 4. The 4th equation you can get by really doing a couple of things. You can go around here, pardon me, start here, go around and up here, back down. And what you're going to get is another equation. The problem is you're going to have to start, it's easy to form a matrix to do this. Wait a second, he gives us V4. I'm sorry, but I made this harder than it needed to be. I just noticed that. Take a look at this. He says V4 is 6 volts, right? All right, now it's game over. Sorry, I didn't see that. I thought we were going to have a system of equations. He gives this as 6 volts. So if this is 6 volts, look how easy it is, all right? With me?
Yes.
Take a look. You all agree this is 10, right?
Mm-hmm.
Yes.
All right, now take a look. Right here, I start here. This is where 4 volts is. I come down here, it's minus V5, right? Follow me?
Mm-hmm.
Yes.
Minus V5 plus 6 is equal to 4, right? Because I'm starting here, so I'd have 4 is equal to minus V5 plus 6, right? And that would mean minus V5 would be equal to minus 2 volts, or V5 would be equal to 2 volts. You didn't see what I wrote, but V5 would be 2 volts. And the only thing I'm doing is once I know this is 6, then if I want the voltage across here, I start at the negative terminal. I can see it's an increase of 6, a decrease of 4, right, to the positive. So I know that V5 would be equal to 2 volts here, 6 minus 4. I've got that. I've got V2. Since I've got this voltage, I have this voltage too, don't I? Because what would this voltage be? Start at the negative terminal. I go here, it's going to be what? A decrease of 6 and then an increase of 12, where this would be 6 volts, wouldn't it, class? Oh, sorry, you can't see.
Yeah, we can see.
Here's what I'm doing. Once I've got this voltage, correct, this 2, right?
Mm-hmm.
Now, if I want this voltage, V2, I'm going to start at the negative terminal V2 right here. It's going to be a decrease of 6. Do you all agree with that?
Mm-hmm.
Joseph, you asked this, right?
No, it was someone.
Who asked this?
It was me, John.
Okay. So this is going to be a decrease of 6 because I went from the plus to the minus, right?
Yes.
And then it's going to be an increase of 12. So that would be what? 6 volts would be V2, correct?
Yes.
Now notice the sign, minus the plus. Now if I want V1, it would be minus 6, right? Then plus 6 or 0. V1 would be 0. right? And that's how we would do it. I didn't realize they gave you V4 6 volts, but once they give you it, the problem's trivial. Okay. Are you guys good with this?
Yeah.
It takes a while, I'll admit. It takes a while to get familiar with it.
Okay, Dr. Baginski, I have one more question if you don't mind.
Go ahead.
Okay, on 2.32 on the homework, I know it's a very simple one.
Go ahead.
But how do you know you can simply just do I times R there?
Well, do you have a current here? It's 4 milliamps.
Right?
How much current is flowing this way?
4.
This way? No. 0, right? There's no resistance. You can't have current flowing off into space, right? It has to flow through something, correct? It has to have a resistance path.
Oh, right. Okay, okay.
That's 0, so it has to come down this way. Current is like water in a pipe. It doesn't just stop, all right? It flows. If you got 4 gallons per second flowing at one point in the pipe, it has to find its way back to the other side of that, and that means it doesn't just stop. So if you have, think of it, gallons per minute flowing there, there's 4 gallons per minute flowing down there, right?
Okay,
Right.
but there's none flowing to the right then.
It can't. There's no resistance here. It's an open circuit. There's no way it can flow. So you got 4 milliamps coming down here. Therefore, you know the voltage here, don't you? Right?
Right, you just do 4 times 6.
Which is 24 volts, right?
Okay.
24 volts is across the 12K, isn't it? Right here. And 24 divided by 12 would be 2, correct? Therefore, 2 and 4 milliamps would be 6 milliamps would be I. Okay.
Okay. Yeah, yeah, I was just asking us for voltage there, so that was my main question. Okay. Thank you.
Sure. Remember, current does not flow off into space. It has to have a path back to where it started or what's causing it.
Okay.
All right.
Thank you.
Sure. I'm looking at 221. Any news about anything going on in Auburn that is not reported by the plainsmen or anything like that? I'm always curious because I should ask the whole classes. Nothing? I read about COVID dormitories that are related to fraternities and sororities. I have no idea what the status of that is.
They've announced I'm sure you saw no tailgating.
Yeah, I know that. There was never going to be tailgating back 2 months ago. We kind of knew that. I'm wondering if we're even going to have a football game though. And I don't have a good answer for that.
Well, I think the tailgating will probably, if there's football, there's going to be people partying up and watching the football game.
That campus is going to be vacant. I can assure you the police will be there.
I mean, like they'll just move tailgating essentially inside of their own apartment.
If there's a football game.
All right, Dr. Baginski, I'm leaving. Have a good weekend.
You too. I'll put up
Thank
some
you.
homework in a bit. You take care. Stay safe.
We will. Thank you.
And let me know if there's any crazy news that's developed that I don't see because I'm not on your side of it. Take care.
Thank you.
Take care. Bye-bye.
Thank you.